All right, this is a little follow-up video using the fcl-image units with ptcgraph units. I've done a previous video where it showed some of the usage, but I've expanded the code and I'm going to go over it again. This will make it more usable basically and easier to manage. But the fcl-image has a lot of useful classes that you can use to manipulate graphics, but it doesn't provide an easy way to display them using ptcgraph, and that's just what I did. So you can see all these formats here. You could use all these formats to read images in, and before you couldn't display them, but with some of my code, you'll be able to display them in with ptcgraph. So let me just show you the code here. It's not very long. If we start from the beginning here, we can see that it's roughly from beginning to end. It's just around 200 lines, 210 lines. So that's not a lot of code for what it does. And I'm just going to demonstrate by using a previous image that I have converted to GIF, and we'll use the GIF reader. We could also do the same example by changing the reader to PNG, but I'm just going to leave that for now because I can demonstrate all the uses for just using this format. You're free to try different images. They should work the same way. So let's just try running the example here. And we can see that we can display the image just fine. And this is using the put image command. So this is something new that I've added since the last video. And basically we have a procedure that converts the FP image to the put image format. And this requires quite a bit of code to support the different formats. So we're handling 8-bit, 24-bit, 16-bit, and 15-bit formats. Everything else below 8-bit still works the same way. It's still regarded as 8-bit. They don't have a different format. They just have less colors. So basically, this covers 16 color modes also. So if you're using VGA, a little manipulation of this code can allow you to support those modes as well. And basically all the other simulated modes. So ptcgraph is just a simulation. Everything's displayed on a 32-bit screen that you have, but internally it stores everything in different different formats to simulate the Borland graphic interface graph functions. So a lot of it is just simulating the old behavior of the Turbo Pascal graph unit. And this is good if you have some old code and you want to convert. Now this allows you to use things like uh, Windows bitmap formats with the BMP format, and even older formats like PCX, things like PC Paintbrush supported. So it just allows you to, like, bring those old programs back up to date if you want to release a 32-bit or 64-bit version or Linux version. And I'm just going to go over some things to try and remember. So when you're using the GIF format, it's important to enable the use palette to true. And what this does, it creates an additional palette that we can set the screen colors to. So this is what this function right here does. The copy FP image palette. And basically, we go through each color that gets created, and we set the screen palette to that. So we do this right here. So we iterate through the loop of possible 256 colors, and we extract the each palette entry, and then we use this function here to convert from all the different 16-bit formats down to 8-bit, and then we use the set RGB palette command in the ptcgraph unit to set the screen colors. Now, if we don't do this, then the colors look all messed up. I'll just comment this out so we can see what it actually does. So if we comment that out, we can see that we get something like this, which it doesn't use the palette information. It just uses all the pixel information, but no color values. This is the default color method. And if we bring this back, we can see that it starts working just fine again. And if we disable this, or let's just change it to false here and see what happens. So we get this if we change it to false. So always remember to set this to true if you're using GIF format. Now, if we decide to change this to PNG, I'm just going to comment this out again, and let's do PNG format, and let's go all the way up to 24-bit, and so we're not using the palette anymore, and I'm going to disable this function here also. So we have it turned off, and we're not copying the palette information. Let's see if it still works using the PNG. Also, we also have to change the readers. So let's go change this to PNG here, and PNG, and let's save it and run it. So now you can see we actually have a much clearer image because the PNG format supports more colors, and we're doing this without using the palette, use palette equals true option. So we don't need to actually copy the palette information. All the palette information is actually stored in the pixel format of the put image buffer. With 8-bit formats, it only stores the index of the color, so that's the difference. So 8-bit formats and lower, the put pixel information is the index of the color. In 15 and 16 and 24-bit formats, the put image pixel is actually the palette, the actual color. So we don't need to, revert to any index. We're just specifying what color it actually is. And I think that about covers it. I could go over some of the code here. So this is where we construct the put image format. A little fancy code here to basically access the buffer in an array format. So we have two different types of accessing the pixel information. One is using long words and the other is using word. Long words are 4 bytes. For word we have to use 2 bytes. So you can see in a 24-bit format, we can, let me just scroll through here. We get the color information, we convert it to a format that we can use with put image, and then we store that information in the array. Doing it this way actually manipulates the buffer, so it's an easy way to access it without having to bit shift or access memory a different way. This is a very easy way. Even though we've only specified an entry of 1, we're like exceeding that. We're not doing any bounds checking, so we're not encountering any errors. So this is just a little trick. If you wanted to manipulate memory, this would be an easy way to do it. You kind of have to like study it a bit to understand what's going on here, but we're just basically accessing the memory through arrays. And the same thing we're doing with the header of the put image format. We're accessing that as a record. So we could specify things like this without having to use the move command or other commands to manipulate memory. And you can see the record for that is just this. It's important to remember that I'm using packed. If you don't use packed, it's not going to work because the way Freepascal and Lazarus use memory, they try to byte align everything for speed. When you use packed, it uses the exact size of all the integers, and in some cases you end up with additional padded space to make everything fit. This way it uses exactly the memory that you want, and that's very important when it comes to graphic formats and manipulating. Everything has to be exact. These functions here for converting formats down, I've actually used ChatGPT to come up with some of this code. I've manipulated a little bit, but like some of all this math, I didn't have to figure it out. It kind of figured it out for me. I just had to test it and make sure it worked. So that's one advantage of using like AI these days. I don't have to spend a lot of time trying to figure out the math. I just need to know that it works. And in this case, it could probably get simplified if I looked at it a bit more. We could probably don't have to divide. We could do a shift and get that same information, but I don't know about any rounding errors. So like I'll just leave it down because it works. And and this is the code here to copy the palette information from the FP image and set the colors on the screen. And this is the original routine that I wrote to display the image pixel by pixel. This is in the first video. It's pretty much the same code. I made some slight changes, but if you want to watch the original video, I'll put a description in a link in the video description so you can watch that. But basically, we're displaying the image pixel by pixel depending on what format it is. So you can see we're displaying here with 8-bit formats, 15-bit, 16-bit. And here I just added a little bit of information like how much byte everything takes. So for 32,000 colors, which is 15-bit, and 64,000 colors, which is 16-bit, we only need 2 bytes to represent that information. But with 24-bit, we actually need 4 bytes. One of those bytes doesn't actually get used, but like that's just the way it works. Okay, I think that's it. I'll end the video here. Thanks for watching.